This is project 5, video number 1, the pencil and paper part. Let's see, we got a coordinate system. Call it X and Y. And you get a bunch of charged particles. Q1, Q2, etc. Let's see how many of them I can draw here. So we got 100 of them. I'm not drawing them all, but I'll draw a bunch of them. That represents a break in the x-axis. But we're supposed to calculate the x component of the electric field at some point P, whose coordinates are given as x comma y. These charged particles are equally spaced along the x-axis with a spacing of 1 centimeter. Alright, so I'm going to pick some arbitrary particle. I'll call it q sub I, and it's at a distance x sub I from the origin, where I is an integer that represents which particle I'm talking about. The first one, the second one, up to the 100th one, and x sub I is the position of that particle. So if x sub I is just I times 1 centimeter. So in other words, if I is equal to 50, then x sub I is equal to 50 centimeters. I times 1 centimeter. And this one particle creates an electric field which is that way. And that electric field can be broken up into components. So draw a vector component diagram. This being the x direction, that the y direction. So there's the electric field. There's E sub x, and there's E sub y, where the electric field is at an angle with respect to the positive x direction, where that angle is the same angle as the angle that the position vector, I'll call it r sub I, of point P with respect to the ith particle. And I didn't come out very well. Alright. So this is the y coordinate of the particle. Every single of the empty point in space point P, where I'm calculating the electric field, the y component for every single charged particle, how high above the x-axis it is the same. It's the same for all of them. The x coordinate of the point in space is the same. It's the same distance from the origin for all of them, but how far along the x-axis point P is away from the particle in question depends on which particle is in question, which particle we're talking about. Okay, so I think I'm just doing some preliminary stuff, but I want to go ahead and get expressions for E sub x and E sub y. E sub x is equal to E times the cosine of theta, and E sub y is equal to E times the sine of theta. So I need that angle, and I can see I've actually got enough information. This distance is how far over point P is. So this distance right here is x minus x sub I. which here's x sub I over to the charged particle, and then the horizontal component of the position vector of point P with respect to the charged particle is this distance right here. So the whole distance over is x. It's the x coordinate of the point in space at which I'm calculating the electric field, and the distance from the ith particle is whatever that total x is minus the x for the ith particle. Let's go ahead and write down the electric field. E, the total electric field, is kq over r squared. So E due to the ith particle, this was the electric field due to a charged particle. So for the case at hand, it'll be the charge of the ith particle divided by the distance that point P is away from the ith particle. So E sub I equals, well, we got a formula where we're given Q sub I is equal to 0.101 times, I'm going to write this down as given, alright, 0.101 times 10 to the minus 6 coulombs minus 0.1 times 10 to the minus 6 coulombs per meter times x. Alright, so the amount of charge of a given particle depends on which particle you're dealing with, and particularly depends on where that particle is, depends on the x value. So I'll consider Q sub I known at this point, and so what I need is r sub I squared. I want an expression for r sub I squared. From Pythagorean's theorem, r sub I squared equals x minus x sub I plus y squared. Well, quantity squared. That 2 goes over there. Alright, by Pythagorean's theorem, that's r sub I. If I ever need, that's r sub I squared. If I ever need r sub I can just write that as x minus x sub I squared plus y squared square root, which highlights the fact that I wasn't supposed to take the square root when I was just writing down what r sub I squared was. There we go. Alright, so I'll consider that to be known. And therefore, E sub I is now known. So I want E sub I, K is a given constant. Q sub I, we got a formula for, so I'm supposed to have evaluated that. I consider that known. R sub I consider known now. So I need E sub I x, which is E sub I. Probably should have called that sub I all along. Let's see if I got that. Yeah, this is just the electric field due to the ith particle, not the total electric field. I'm just depicting the electric field due to the ith particle. Okay, you're getting there. E sub I times the cosine of theta. That's all I needed. I wrote down y is equal to E sine theta. That's extra. We don't need that because all they're asking for is the x component of the electric field. So I got to get the cosine of theta. Theta, I could say, is the arctangent of y over x minus x sub I, but I'd prefer to replace the whole cosine of theta as opposed to just the theta. And from this diagram we see that the cosine of theta, that's for the ith particle. It's the particular angle that this position vector makes. Position vector of point P with respect to the position of the ith particle, so that should be a sub I as well there. So I'm going to put that on there. Let's see, do I have that down here? Yeah, that angle theta is specific to which particle I'm working on. So I better put a subscript on it. Now the cosine of that angle for that particular particle is equal to the adjacent x minus x sub I over r sub I. So I could consider cosine of theta known, but I actually feel like substituting that in here. So e sub I x is equal to k q sub I over r sub I squared times, and it was something over r sub I. It was x minus x sub I, but I better check. Yeah, x minus x sub I over r sub I. So that gives me the electric field due to the ith particle, any one of them. You have, for the first one, it would be r sub 1, x sub 1 there, and r sub 1 there, where all these things are known. So x sub 1, for instance, would be the distance from here out to whatever you chose for x, so x minus x sub 1, and that helps to determine what theta sub 1 would be, and r sub 1, etc. And we do it for 2, 3, etc. I'm going to simplify this just a little bit. E I x equals k q sub I. It doesn't look much like a subscript sub I there, but now it does. Not sure it does here though. Alright, let's try to make that look like subscript I. K, that's a lowercase k, q sub I times x minus x sub I, all divided by r sub I cubed. And then e sub x is equal to the sum I equals 1 to 100 of e sub I x. So the total x component of the electric field is the sum of all the individual x components. I just add them like numbers. I couldn't add up the e's like numbers because they're vectors and they're pointing in different directions, but I can add up the x components, and I can think of it as adding up the x component vectors because they're all pointing in the same direction. Alright, that was part of the reason that I found the x components. The other part is because they're asking for the x component. So I think I got everything I need. I might just have to number those equations as I go along. So 1 I'm going to accept. x comma y as arguments. So I'm given those values. Initialize some variables. So for instance, I gotta say k is equal to 8.99 E9 Newton meter squared per Coulomb squared, but the computer the units are implied here. The computer doesn't understand the units. I think I'll call that all the initialization, but I'll leave myself a little room just in case I'm forgetting something. I'm going to say x equals linspace from 1 to 100 in 100 steps. I think that's what it was, 1 to 100. No, in steps of 1. Oh, no, I forget. I think it's, I need 100 of them. So, might have to, I think I'll do it by trial and error, but, might have to fix that up I might not have the right idea on linspace, but my idea is I want to get, 100 values. X is going to be an array of 100 values from 1 to 100. Ooh, I think, I'll put everything in meters right off the bat. So from 0.01 to 1, and 101 values from evenly spaced from 0.01 to 1. Alright, I'm not sure that decimal point is just the right spot to make it look like 1.00. Okay, now it does. So then I'll make Q an array of 100 values as well, and I'll say Q is equal to 1.01 times 10 to the minus 6 minus 1 times 10 to the minus 6 times x. That I'm using the given expression for Q. Alright. So now I've got all the positions and I got all the Q's. And let's see if I'm ready to get... Oh, how about the R's? So I've accepted x and y as arguments, so they're known. They're two values, one value of x and one value of y. And then they're the coordinates of the empty point in space where I'm calculating the x component of the electric field. So I'm going to say R. It's going to be an array too. It's going to be an array as well. And it is equal to the square root of x minus, I've got two expressions, two meanings for x. So I'm going to let this be xp and yp, the coordinates of point P. And ahead, x is being the x coordinate of point P, and x is being an array of all 100 x values for the charged particles. And can't do that. So this will be xp minus x. And then that's got to be squared. I think I got to go dot power 2 because it's an array. You know, I got XP as a single point, but I subtract each value of the array X. I'm going to have 100 different expressions for XP minus X. That's an array, and I want to square that on an element by element basis. And so for the first element, for instance, I want to square it for that one value, and then I want to add y squared. I'll go ahead and put that down as y to the power of 2 as well. That I don't need the dot because it's just a single value. The dot doesn't hurt if it's just a single value, but I feel like leaving it off. Alright, so now I got 100 values of r. And I think I'm ready to use this expression. KQ x over r cubed. I'm going to try 6. E is equal to, E equals K times Q times X minus X sub I. There's got to be a dot star. I'm going to put dot star here as well. I don't think that matters because I'm just multiplying by the number K. I changed my mind on that. I'll just make that a star. If it doesn't work, I'll figure that out at the time. And this is dot slash R. So I'm getting a little carried away here, like putting it down as MATLAB expressions when it would be okay to just write it as the generic expression. I'm thinking ahead to try to make the coding a little bit easier. And then this needs to be cubed, and it's an array. I want to cube each element. So KQ x difference divided by r cubed. Is that what I had? KQ x difference divided by r cubed. And then that's really EX as opposed to E. I think I'll go EX total equal the sum of all the EX's after that. Alright. Seems like I got to declare the function at the start, but I think this is a reasonable outline of my code. And I got to remember I am returning something this time, so I need to include a return variable. So this is my code outline. And I think I've cracked this problem. Just a quick review. It wanted us to find the electric field X component at this point due to all these charged particles. So for each charged particle, I find the contribution to the electric field it makes, and then multiply that by the cosine of theta to get the contribution to the X component of the electric field that it makes. And then once I've done that for each of the particles, I add up all the X components and I have the answer that they're looking for. Alright, EX total. Alright, I think that's a wrap for Project 5, video number 1. Remember, I wanted to experiment with this lens space, make sure I've remembered that correctly. And so sometimes I do have to come back as I'm doing the rest of the project and modify the pencil on paper part. Be aware of that. So if I've got a mistake in here, make sure that if I correct it somewhere along the line, it doesn't wind up in your final version.